Toronto has long been a city defined by its skyline, from the CN Tower to a forest of gleaming high-rises. Each generation has added new icons to the city's architectural story. At one of its busiest intersections, where over 200,000 people pass through every day, rises a new icon, One Bloor West. When complete, this 85-story tower will stand over 300 meters tall, making it Canada's first super-tall building. But behind its striking architecture lies a story of structural innovation, made possible by advances in high-strength steel. Welcome to the ArcelorMittal International Channel, where we talk all things structural steel. The developers had a bold vision: create Canada's tallest tower while also delivering an extraordinary retail space at its base. That meant a 30 by 30 meter column-free space soaring 12 meters high, a cathedral-like volume in one of Toronto's most valuable retail districts. In order to make this happen, the team first considered a steel diagrid exoskeleton. Although the diagrid system is striking, it was ultimately cost-prohibitive in Toronto's market. A fully concrete tower, on the other hand, couldn't deliver the openness needed at retail levels. The structural engineer for the project, RJC, came up with a different idea: a composite system. Reinforced concrete above, paired with steel struts and megacolumns at the base. This hybrid approach provided strength, flexibility, and efficiency. Here's how it works. The building's vertical and lateral loads are carried down through its exterior columns and interior concrete core. Starting at level 5, the loads from the core are transferred into a series of inclined steel struts, which redirect those forces to the composite megacolumns at level 3 and the ground floor. Rotating the structure gives us a clearer view of the system. There are 8 megacolumns in total, 2 along each face of the building. The braces from adjacent sides converge at large fabricated nodes located at the 3rd and 5th levels. This design strategy eliminates the need for interior columns or a central core within the retail levels, while still delivering the stiffness and stability required for an 85-story super-tall structure. Connecting all of these massive forces required an equally innovative approach. For the nodes at the intersection points of the inclined struts and megacolumns, the design team turned to Cast-Connect's high-integrity blocks, each weighing up to 50 tons. These custom-forged components serve as precision interfaces, transferring the immense forces from the struts into the megacolumns while maintaining strict geometric alignment. Working closely with the steel fabricator, the Walters Group, the team paired these nodes with high-strength steel sections from ArcelorMittal. This approach allowed the assemblies to be fabricated off-site, shipped to site as complete units, and lifted directly into position, ensuring both strength and constructability in one of Toronto's most complex building projects. From below grade up to level 9, the megacolumns anchor the inclined struts and carry the full weight of the structure above. They are the true backbone of One Bloor West. Each column bears up to 290 meganewtons of load, the equivalent of nearly 30,000 metric tons. Structurally, they combine 4 high-strength A913 steel sections, surround them by high-strength rebar, and ultimately encase it all in 75 megapascal self-consolidating concrete. This approach combines the stiffness of concrete with the strength of structural steel, enabling extremely high capacity within a compact footprint. At the time of design in 2017, the use of A913 in this type of composite system was entirely new in Canada. Existing codes offered little guidance for elements of this scale and configuration. The Canadian Institute of Steel Construction standards impose conservative limits on material strengths: 55 MPa for concrete, 350 MPa for steel, and 400 MPa for reinforcing bars. To justify the design, RJC compared baseline CISC provisions to international references and emerging composite design literature. Additionally, no code directly addressed the behavior of columns containing 2 or more encased steel shapes. To fill that gap, experimental testing and numerical modeling were carried out in 2015 through a collaboration between the Council on Tall Buildings and Urban Habitat, ArcelorMittal, and industry partners. This led to a simplified design methodology, validated against global standards, providing a foundation for the system ultimately used at One Bloor West. This combination of research and advanced materials is what made the system possible. And at the center of it all, A913 high-strength steel. Unlike conventional grades, A913 is produced using a quenching and self-tempering process, or QST, which refines the steel's grain structure. The result is exceptional strength, up to 80 KSI, or 550 MPa, combined with outstanding weldability. For One Bloor West, A913 Grade 65 provided the ideal solution. It allowed the team to design smaller sections and reduce steel tonnage. While this saved on cost, it also provided another critical advantage in constructability. The largest crane picks on the project weighed nearly 47 tons, or over 103,000 pounds. With a maximum crane capacity of 50 tons, or 110,000 pounds, the megacolumns were pushing the limits. The use of high-strength steel reduced the weight of the steel sections by nearly 25%, making the crane pick possible. If standard steel were used, it would have required a much more costly and complex erection procedure. A913 also has a proven track record across Canada. It's been used in several tall buildings, such as the Bay Adelaide West, East, and North Towers, 81 and 141 Bay Street at CIBC Square, and 160 Front Street, each project demonstrating the same benefits: reduced tonnage, ease of fabrication, and improved efficiency. By applying these lessons on a new scale, One Bloor West shows how high-strength steel can help redefine what's possible in tall building construction. Lastly, compared to a reinforced concrete column, the smaller footprint of the mega column was able to maximize space at the lower levels. At the ground floor, an equivalent concrete column would measure 2.5 by 2.5 meters. The composite mega column, only 1.8 by 2 meters. Overlaying the two options, that smaller footprint of the mega columns gains 2.65 square meters, or 28.5 square feet per column. When we account for all columns and the third and fourth floor retail levels, it's over 48 square meters, or 519 square feet, of additional rentable space. In Toronto's luxury retail district, that's a gain with enormous long-term value. That's all for now, but there's still more to this story. To learn more about the mega columns, foundations, aerodynamics, mass dampers, and other design features, check out the full case study, available on the ArcelorMittal International website.